MOISE is a collaborative project conducted by the IRT Saint Exupéry, focused on the aerospace domain. It brings together industrial companies, consulting firms, tool vendors and public research institutes around a common goal, to develop collaborative model-based approaches for system engineering in the extended enterprise. When developing complex systems, partners of the extended enterprise have to exchange and process tons of engineering data, most of which in a text format. Through a greater use of models, the project aimed at improving the efficiency of information sharing between companies and across engineering domains. By providing means to achieve seamless co-engineering, we help reducing misunderstandings, design iterations, and ultimately development costs. The project tackled 4 thematics. 1. How to exchange and aggregate heterogeneous modeling data across the extended enterprise. 2. Ensuring consistency between safety analysis and system definition models. 3. Generation of a co-simulation environment based on the system architecture description. 4. Improvement of the need elicitation using models in a customer-supplier relationship. To be certified and be allowed to fly, aircrafts and embedded systems must comply with airworthiness regulations. Safety teams support certification activities. They assess the system conformity with safety requirements, and make sure the system fulfills its functions with the appropriate level of confidence. System architects have to take into account different points of view during systems development. In order to successfully integrate all constraints and requirements, they need to rely on an efficient process. In particular, it is critical to manage the risks related to safety aspects as soon as possible and all along the development. Usually, during development of critical systems, the system definition and the corresponding safety assessment are performed by different teams. Information is available in textual or informal graphical form. Based on provided system description, fault trees models are created by safety specialists to support safety analyses. These safety models are then validated during reviews involving both system and safety engineers. These reviews provide the necessary level of confidence to perform the architecture safety assessment. This is a highly iterative process. Besides, the use of different data formats for requirements and fault trees models causes communication issues between both teams, and makes it difficult to efficiently validate safety models or to trace the outcomes of the reviews. In this context, keeping track of system modifications and maintaining the consistency between the safety analysis and the system definition is a complex task. Inconsistencies between the safety models and system definition can result in overdesign due to misunderstandings or unnecessary conservatisms, additional iterations, leading at worst to late design changes, and finally, in a loss of confidence in safety assessments. MOISE project developed a model-based methodology allowing to maintain the consistency between a system description model and a safety propagation model. Models' elements, such as functions, are explicitly linked and traced by the synchronization points. During reviews, these synchronization points are examined by the system architect and the safety specialist, and possible structural discrepancies between models are commented and justified, in order to guarantee that nothing is inconsistent. When the system architect modifies the architecture and releases a new version, for instance, after having added of a new function, or refined the MBSE model, it is possible to detect and indicate that changes have been performed. Then the safety engineer knows where he may need to update the safety model. Safety model reviews are structured in order to identify whether or not the two models are consistent, and outcomes of the review are formalized. Once the physical architecture supporting the functions is added to the system model, and similar synchronization is performed at the physical level. In the end, functions, sub-functions, allocations, equipment and interfaces are synchronized. From the safety assessment point of view, we provide an analysis at both functional and physical levels, and we link equipment failures to functions and corresponding failure conditions. In summary, We propose an innovative model-based synchronization method to efficiently assist system design and safety analyses consistency reviews. This method is supported by methodological guidelines for MBSA modeling and assessment, and has been successfully validated on a representative study case. This work will be continued in a new project led at the IRT Saint Exupéry, called S2C for Model-Based System and Safety Continuity. MOISE project also produced transverse outcomes that supported our activities. A study case of a drone for aircraft pre-flight inspection. It is composed of architecture models, safety models and behavioral simulation models, some of which are open source and can be downloaded from the IRT Saint Exupéry Forge. A glossary, or more precisely an ontology for more than 300 terms relating to system engineering, constituting a valuable common reference. And is part of our state-of-the-art review is structured databases of 230 ID cards for MBSE methods, languages and tools that can be accessed online by our project members. Thank you for your interest, and do not hesitate to contact us for further information.